Good day, everyone. Welcome to the Embedded Software Development course. Today, we'll be talking about bit shifting, specifically the left shift operation. Just like other bit manipulation techniques we've discussed, we can apply bit shifting to register manipulations, which we will discuss in the next section. But for now, let's talk about left shifting. So it's a very simple operation. It's all about shifting the bits of a particular number to the left. So suppose we have a binary number, an 8-bit binary number, 00000001. And we want to shift the bits of this binary number to the left by one position. It's a very simple process. All we have to do is take each bit and move it by one position to the left. So what I'm going to do now is I am going to shift this binary number to the left by one position, and the notation for that is 1 left shift 1. So this 1 here stands for the number that I am performing the operation on, and this second one stands for the number of positions or the number of shifts. Okay, so when I perform the operation, my bit 0 is 1. I shift it to bit 1. So there's nothing at my bit 0 again. I just put a 0. And I repeat the operation for other bits by shifting them to the left by one position. Okay, so I'm shifting to the left by one position. And finally, I shift the most significant bits to the left by one position. So if we count the number of bits we have, 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 9 bits, but we're using 8-bit storage, right? So for an 8-bit storage, we would disregard these most significant bits. So this will be the results of the left shift operation. And this binary number, when you convert it to either decimal or hexadecimal, the value is going to be a 2. So 1 left shift 1 equals 2. Okay? So let's try 1 left shift 2. What is 1 left shift 2? To get 1 left shift 2, all we have to do is perform the left shift operation one more time on this result that we got. So we know 1 left shift 1 gives us 2, this binary number. So we're going to perform the left shift operation on this result to get 1 left shift 2. So we have 0, 0, 0, 0, 0, 0, 1, 0 as the result of our first shift. So we perform the left shifting again. So that's saying 1 left shift 1, and then we're performing another left shift operation. So that is going to be 1 left shift 2. So I shift this bit by one position to the left. It means that my bit 0 is now vacant, so I can put a 0 there. I shift this to the left by one position. I shift this to the left by one position. I shift this to the left by one position. Shift this by one position, and this by a position to the left. Shift this by a position to the left, and finally the most significant bits. So by the time you count the number of bits, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. And since we said we're using 8-bit storage, we will disregard this most significant bits, and this is the results. So 1 left shift 2 is going to give us this value in binary, and by the time you convert to hexadecimal or decimal, that value is going to be a 4. So if I have my original number as 00000001, shifting it by 2 positions to the left, shifting its bits by 2 positions to the left would give me 00000100, and you can actually see it here. It's very obvious that the bits at bit 0 was a 1, right? That particular bit, or that 1, is no longer in bit 0, it is now in bit 2 because it has been shifted by 2 positions to the left. So that is how simple the left shift operation is. So let's try something a little bit more challenging. Let's try 0x34, and we want to perform a left shift by 3 positions to the left, okay? So in binary, let's assume we're using 8-bit storage. In binary, this number is 0011 0100, okay? So I'm going to perform the left shift operation 3 times. So if I do the left shift operation for the first time, that's 0x34 left shift 1. So I'll shift all the bits by 1 position to the left. So I start with the bit 0, I shift it to the left. It is now in bit 1. So my bit 0 is now vacant. I just put a 0 there. I shift this also. I shift this. I shift this. I shift this. So this is now 1. I shift this. This is 1. I shift this. This is 0. And finally, I shift this. This is 0. So if I count the number of bits, that's 1, 2, 3, 4, 5, 6, 7, 8, 9. 8-bit storage will truncate the most significant bits. And this is what we have for the result of our first shift operation. So we shift this again, we shift this result. So the second shift makes it our original number shifted to the left by 2 bits. So if we okay, let me take away those underscores. Sorry. Yeah. So we know that shifting this again is the original number shifted to the left by 2. Oh, I said underscores. I should have said something else, but never mind. So let's shift this bit to the left by 1 position, right? Okay. So our bit 0 is now vacant. We put a 0 there. We shift this to the left by 1 position. So we have a 0 here. Shift this to the left by 1 position. We have a 0 here. Shift this to the left by 1 position. We have 1. And we shift this to the left by 1 position. We have 0. Shift this to the left by 1 position. We have 1. Shift this to the left by 1 position. We have 1. And finally, we shift this to the left by 1 position. We have 0. Count the number of bits: 1, 2, 3, 4, 5, 6, 7, 8, 9. So we truncate the most significant bits. We perform the shifting one more time. So shifting this results by 1 bit to the left, or 1 position to the left, it means that will be our third left shift operation, which makes it our original number shifted to the left by 3 positions. So we pick these bits and shift to the left, we have 0. We pick these bits, shift to the left, we have 0 here. Pick these bits, shift to the left, we have 0. Pick these bits, shift to the left, we have 0. Shifting this to the left gives us 1 here. Shifting this to the left gives us 0. Shifting this to the left gives us 1. Finally, shifting this to the left gives us 1. But do not forget that since we shifted the first bit to the left, that particular bit is no longer in bit 0, but is now in bit 1 position. So our bit 0 is vacant. We put a 0 there. Should have done that in the beginning. So counting number of bits now, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we truncate the most significant bits, and our result is 1010 0000 in binary. So 3, 4 left shift 3 gives us this result, which is also A0 in hexadecimal. Okay, so we've been able to explain how the left shift operation works, and it is going to be very useful in upcoming lectures. So that's all for this video, and I will see you in the next one.